we have a gas laws stoichiometry combination
That's
lab.
right. I mean, this is great because it's a mix of gas laws, stoichiometry.
Yep.
There's a little bit of everything coming at you. And actually, we've already used this reaction once in a lab. What we're going to do essentially is heat baking soda, which is sodium bicarbonate, NaHCO3, and when we heat it, it decomposes. And it gives off carbon dioxide gas as one of the products. The lab sheet has the equation, the reaction on there for you so you can see it. Okay, so the gas you're going to be seeing produced is carbon dioxide. That's where the gas laws fit in. Okay? Now, to be able to do stoichiometry, of course, we need to know what mass of sodium bicarbonate are we starting with. So let's start there. Mr. Moore has already put some out in a weighing dish, but let's get a mass for you. Okay, so we zero our paper.
I wanted to at least do something for the lab, so I measured out a gram of baking soda.
Mr. Moore is doing most of
Trying to
this.
be helpful.
Okay, there's our starting mass of sodium bicarbonate. Okay. Now we're going to heat it in a test tube. So I'm going to transfer this into this test tube we've got set up over here. Okay, so we got most of it down to the bottom.
That's not very much, Mr. Hubble. I hear in chemistry more is better.
More is better. Absolutely.
But yeah, 1 gram, I guess we'll go with that.
We'll go with that. Okay, so that's pretty much ready to go and start heating. Now, we're using a technique to collect the carbon dioxide, which is called collecting the gas over water. And so the idea is that we have a tray here that is about half filled with water, and there's a rubber hose connected to a stopper. This will fit into the test tube. And when we start to heat the sodium bicarbonate and the CO2 is generated, it's going to come through the tube and it's going to enter the bottom of the tray through a hole in the bottom.
Oh, yeah.
Okay, so we'll start to have bubbles of gas coming up from this hole. All right, but we want to collect it. And so to do that, we're going to collect it in a jar. If we wanted to be fancy, we'd call it a gas collection jar. All right. And so what we're going to do here is we filled the jar with water so that we can measure its total volume. All right, so let me do that next. I filled the jar to the top with water. Hopefully I can transfer without losing any. This is going to give us the total volume of our gas collection bottle. I don't have my glasses on. This could be hard to
Almost 300. See, we're using this because we can get it all in there at once. Just under the 3. So you can kind of see how this thing is graduated. 250 is down below. It's between 250 and 300, much closer to 300. Looks like it's right about that last line.
What is it, like 280? I don't remember.
I want to say it's 290 or 295.
Okay.
It's 295 or so.
Okay, so let's say you might have trouble seeing it. 295. Now that's milliliters of our jar.
Yep,
filled tip top.
Total capacity of the jar. Yeah.
Okay. Now the idea is that the gas is going to bubble into here and it'll push some water out. You'll see this happen. So we'll measure the volume at the end, the water that's in here, and then the difference is going to be the volume of gas we've collected.
Mm-hmm.
Okay? Now we need this jar to be filled to the tip top.
Right, so we start with no air in it.
Right, we don't want any air in this thing to start with. And hopefully I've got enough water. See, some water could remain stuck in the graduated cylinder.
When you guys are all here in school, we always tell you to fill it up so that the water is actually bulging out the top.
Right. To make sure, I'm going to try to add just a dash more water. We might have lost some in the big cylinder.
You see, the surface area kind of holds it together like that. Yeah, that's good.
Pretty cool.
Yep.
Okay, so now what's going to happen is I'm going to slip this glass plate over the top, hopefully in a way that'll prevent any air bubbles from being in there, which I think I managed to do.
Yep.
And I'm going to invert it into the tray of water and slip the plate out. So if you do this right, you end up with the gas collection bottle upside down, completely full of water with no air bubbles.
Looks good.
Okay, so it's ready to collect the gas. The idea is that we'll slip it over that hole in the bottom of the tray. As we start collecting gas, it'll bubble in.
Mm-hmm.
Okay? Shoot, you want to measure temperature now or later?
Now it's good.
Now it's good.
Yep.
All right. So the water, excuse me, the water here has been sitting out. It's at room temperature. We're assuming the gas we're collecting, the CO2, is at room temperature. And so this is Mr. Moore's favorite blue thermometer.
Love
this
this
thing
blue thermometer.
is
Can you rotate it
laser
away from you just a little bit? Okay.
laser accurate. What place should you be reading to here, by the way?
Looks like it's graduated to the 1 degree place.
Yes.
Oh man, I'm having trouble focusing on it. Sir.
It's probably because I'm moving. If I do
Okay.
this, does that help? Probably still wobbling it back and forth.
Yeah, and I'm moving the camera too. We can see, yeah, I mean, it looks like it's right on one of the lines, so that's not going to be too tough to read.
Okay.
Okay, so that will represent the temperature of the CO2. Right.
Now, we're going to also want to know pressure, okay? So we've talked about a barometer in class before. Okay, this is our barometer we always use for this. It's measuring the air pressure in the room. I don't know if I have it rotated. Now, this is a little confusing. It's got an outer scale that's reading pressure in inches of mercury, which is what your meteorologist would do. Like when you listen to the weather, they might say, oh, the air pressure today is 29.2 inches of mercury and falling, or whatever.
Mm-hmm.
Okay, well, we'd prefer millimeters of mercury, all right? And I don't have my glasses on. Is it the inside one?
No, we're going to have to read the outside one and then convert it to millimeters.
Okay, that's this, because we have
Yep.
different.
Yeah.
Okay, so in the end, you're going to read this pressure. It's going to be in inches of mercury, and we'll convert it to millimeters later.
Okay, so yeah, you can see here's 30, 30, and then 31 is down here. So between 30 and 31 is closer to 30. Ignore this is just so we can kind of keep track and see if it's going up or down. Looks like it's just over 31. So try to read that as well as you can. This is inches of mercury. So once you read how many inches of mercury it is, then we have to convert it to millimeters of mercury by multiplying by 25.4. I got a little set of instructions down here.
Yes.
So yeah, take the inches, 31 point whatever, and multiply by 25.4. That gets you millimeters of mercury for the atmospheric pressure. Got it?
Okay, I've been able to read it.
Yeah.
Now, here's another little fun fact. There's all kinds of little things going on in this lab. Remember, when you collect the gas over water, the gas that's being generated is not by itself. All right, because water evaporates. There's nothing we can do to prevent that. So we're going to make CO2 gas. It's going to bubble in here, but evaporated water is going to mix in with it. And so we need to know the vapor pressure of water, because I know the total pressure that we just read is the sum of the CO2 pressure and the water vapor pressure.
Mm-hmm.
And in the end, when we do our calculation, we want the pressure of just the carbon dioxide. So we've got this little chart here. We know the temperature. The vapor pressure depends on the temperature. So
The warmer water gets, the more it evaporates, the higher the vapor pressure.
Yep.
So just use the closest vapor pressure to what the temperature was.
Yep.
Okay.
Okay, we got that. Now, I think we got all the preliminary data, right? We're ready to go
I think we've
here.
got it, yep.
All right, so again, the idea is we'll start the burner, we'll start to heat the sodium bicarbonate, we'll start to decompose, it'll make CO2, and then we're going to try to capture it in our gas collection jar. Okay?
Let's fire it up.
Fire it up. Okay, so, oops, you know what I didn't do, Mr. Moore, did I set this in here, but I never,
Oh yeah, got to make it nice and tight. Sometimes we,
yep, I did not really mash it in there.
okay. Yeah, sometimes it's not set in there well and you don't
Yeah.
ever get the bubbles.
Yeah, okay. So we're starting to heat it. Okay, at some point it's going to start to decompose here.
All right, bubbles happening. Oh my goodness, there they are. So that's our CO2 being generated. Can't really see anything happening in the test tube, can we? I mean, it does make sodium carbonate from sodium bicarbonate, but it pretty much looks the same.
Yeah. They're both white.
So we can tell something's happening from that.
Now we're assuming when the bubbling stops, the reaction's completed. So.
Yep. One of the other products of this reaction is water. Water vapor comes out. In fact, we may be able to see some water.
You can, inside the test
Look
tube.
at the top of the test tube underneath that stopper, and I see some drops of water, and that's one of the products of this reaction.
Now it's not a big deal if some of the water vapor that's produced comes into here, because it's just going to mix with the other water.
Uh-huh.
And in the end, it doesn't affect our calculation. Seems like it's starting to slow down a little bit.
Yeah, it's still bubbling pretty good,
Still
but
bubbling.
it is slowing down.
Should have had a good chemistry joke at the ready here as filler.
Yeah, I know.
Material.
This dead air
Sorry.
will never be good on TV, will we?
Yeah, no.
Got to keep chattering to keep the audience interested.
Yeah. Now, one thing too that's always kind of interesting is as soon as you pull the flame away from the test tube, when it starts to cool, the pressure goes down inside, and you can actually suck water back into the tube, which is bad because you got hot glass with cold water, and so you have to be careful to disconnect this once you stop heating.
Yep.
Because you can't.
We've
crack
broken
the test
plenty of test tubes doing this.
Yeah.
Yeah, absolutely. It's a Charles Law thing. Charles Law goes both ways. When you cool a gas, it tends to contract, and with the water at the other end of that tube, it'll contract and pull the water right up to it.
Yeah. And you see, you
Oh, we
think
got
it's
sudden
almost
surge.
done, and then it all of a sudden you get a flurry of bubbles.
I keep thinking that we're
there we
done,
go.
and then we get this.
If you like to bake, right, this is significant, right? You ever talk about why bread rises and whatnot? Because it's CO2 gas production that does it.
Yeah, in breads and cookies and cakes, you've got little bubbles, right,
Mhm.
that are formed because of the
Yeah.
CO2 being made.
Okay, every time I think it's about done, we get a bubble.
Come on. Are we there? Oh. Oh,
Big flurry. Seen one here for.
I think we're nearing the end. Or maybe have gotten to the end.
Little bubble.
Are we good?
Seems like
Had
it.
enough of this?
All right, well, it seems like it's pretty well done.
Yep.
Okay, so we're going to cut the heat, and I'm going to unhook the stopper, because again, we don't want to suck cold water back in. So now we got one last job. We're going to try to get the jar out of here without losing any water.
Yeah, so we can find what volume of the CO2 was made by determining the difference between the amount of water that's in it now and how much water the jar would hold total.
Okay, so there we go. I don't think it's going to fit in 100.
I don't either. Yeah, let's just use that one
We have to
again.
go back to our bigger cylinder. Okay. I don't know if my hand helped at all.
I think it does, yeah, having that black, dark background. So yeah, between
Is darker better?
150 and, oh, yeah, that is better. Between 150 and 200, looks like we're just shy of 175, so let's go with 170. You guys agree? 170 ml? Yep, that's good. 2 sig figs, I mean, for a plastic graduated cylinder like that, I can live with 2 sig figs.
Yeah. So I think that's all our data. Right now,
I think it is.
ultimately, what you're trying to do is calculate the percent yield based on how much CO2 we made.
That
So
sounds right.
It's a great mix of gas laws and stoichiometry. Twice the fun.
Well done, Mr. Hamel, thank you.